Thanks, Josh. And thank you all for this opportunity to present. I'm Robert Donaker. I'm with TangiTek, Tangible Technologies. We're a startup company in Portland, Oregon, and the whole company's here today. There are three of us. So you get everybody today. And I'm going to present this project called Magnetic Carbon Fiber Radar Absorbing Materials. We call them MFRAM. And what we're doing is absorbing microwave energy. If we talk about EMI shielding, there are two major classes. I can either reflect electromagnetic energy back to you, or I can absorb it. And we're working on the absorber part of the energy. So the wave comes in, hits our material, travels into the material, and the energy is absorbed within the material. So there's very little reflection off the surface or radar return from these materials. And how it started, we were working on another SBIR project. My background is fluid mechanics, and I was developing a remote sensing system to validate my hydrodynamic models. And we were developing a remote sensing platform, and this is 15 years ago. And we were using helium balloons to launch an aerial platform, an infrared camera. And I was looking at industrial and signatures. You always want to make your platform lighter and lighter. So we went from an aluminum robotic camera mount to a carbon fiber camera mount. And we were just using off-the-shelf Wi-Fi equipment to transfer data to the ground and control our cameras. And we constructed this beautiful lightweight camera mount out of carbon fiber. And all of a sudden, our radios stopped working. And we took everything apart. They all worked, put it back together. They stopped working. And so we realized this carbon fiber had a real strong effect on the electromagnetic energy that we were trying to control the platform with. And turns out carbon fiber is pretty reflective in microwave energy spectrum. So you build bicycles, airplane kind of stuff. It almost looks like metal when you bounce a microwave energy off it. Very reflective. And so we became very interested in manipulating the properties of carbon fiber to see if we could get it to absorb energy. And so that's what MFRAM is a materials technology where we alter the structure and kind of form of the carbon fiber to make it absorb energy rather than reflect it. So it's a metamaterial, combines carbon fiber. This is standard old carbon fiber that you build bicycles and airplanes and whatever. It's chopped up into small fibers, which are called flock. And what we're doing is we're depositing these small fibers on an adhesive surface by the process of flocking, which is merely electrostatic deposition. And what we're trying to do is make something that looks like carbon fiber velvet. So most textiles are kind of woven in the XY plane, and we're depositing these fibers in a more or less vertical orientation. So it looks and feels like a velvet textile. As a matter of fact, if you have a high-end automobile, they flock the interior surfaces of the console and the glove box as a sound. It's an absorber of sound, and also your cell phone doesn't, fly across the dash, or your change doesn't rattle across the glove box. It gives you a kind of a rough, textured surface. So you've probably seen flock, whether you realize it or not. So here is Kent in the lab flocking carbon fiber. We can produce this material, and I call this bench scale maybe 1 foot by 1 foot square samples. So he's flocking the carbon fiber, and then we do some additional treatments to the carbon fiber to enhance its absorption capability. We first thought just flocking it would help a lot, and we ended up with a very mediocre absorber. And so we realized very quickly that to make it a stronger absorber, we had to add other materials. So we Further, we coat these carbon fibers with dielectric materials and then magnetic materials, and what we're using right now is zero-valent iron microspheres, so it's a nanomaterial, it's just a very fine type of ferrite. And what you end up with is a structure that kind of looks like from the side kind of a dewy turf or something. So these fibers that are more or less vertical, they're coated with insulative material, and then they have these magnetic particles. And what it ends up being is those carbon fibers are more or less acting as antennas. They're all little antennas that conduct microwave energy pretty well. And the magnetic particles are like magnetic chokes, very similar to those round cylinders you see on power cords that go into your computer or other monitors, other electronic equipment. And what those are ferrite chokes to kill any signal that is picked up by your power cord. Your power cord is the big antenna, and you don't want to inject a bunch of star chassis. So we're doing that in micro scale. This is not nanotechnology, this is micro scale technology. So what we started was to create a broadband absorber, 1 to 40 gigahertz. We wanted to minimize these absorbers, but something that was relatively thin, flexible, breathable, have very desirable physical characteristics beyond the strong microwave absorption. And in the commercial market now that we can find out about, there are two major classes of absorbent materials. One would be dielectric materials. These are generally foams. If you've ever seen an anechoic chamber, I'll show some pictures. Large pyramidal structures, and they absorb energy by, but they tend to be broadband, they're light, and they have absorption properties. Second major class are magrams or magnetic absorbing materials. This is first developed in the 1940s when the Germans were trying to hide their submarines. The Allies very quickly realized they could spot snorkels and periscopes with radar, and the Germans realized that we have to coat these so we can't be found, so they developed these magrams to absorb the energy. So magrams have been around for a long time. The downsides of magrams is they're very heavy because they're loaded with ferrites, which are heavy. They can be fairly thin sheets, but they tend then to be fairly narrow band. So you have these two worlds, thick, light, very bulky, narrow band, or broadband, and there are the magrams, which are thin, but they're heavy, and their frequency response is usually fairly narrow. So we developed what we call a hybrid metamaterial solution, which is this magnetic carbon fiber flock, and we call it MF-RAM, and I believe from our assessment we're probably at TRL 4 or 5 now, depending on the application, and I'll give demonstrations. So that's what we're doing. And so successful phase 1 BIR proposal. We wrote that to characterize the material. We want to create an EM model of the material. We want to be able to model it. And with help from Portland State University, they have an anechoic chamber. And in the chamber there on the top right, we're doing what's called an NRL arch test, Navy Research Lab arch test. It's a test of the absorption of a material. You have a transmit antenna, you have a receive antenna. You send a signal out and bounce it off the material and see what comes back. It's kind of the proof of how good your absorber is. And so we used a number of techniques to extract the complex permeability and permittivity. These are the basic. So we were able, and the absorber itself has pretty unique characteristics in the sense that it can have very strong broadband absorption. We've observed greater than 40 dB peak, which is 0.999% of the energy. It's very high. And we've tested in KU band to greater than 30 dB. And because we're using these carbon fiber flock, these little pieces of carbon fiber, we can vary the length of the flock. We can vary the amount of magnetic materials we put on, and we kind of can tune the absorption response of this material, whether you want it higher or lower, by controlling the loading of how dense the flock is, the lengths of the flocking materials, and the amount of magnetic materials. We can kind of tune that response depending on where you want the sweet spot of absorption. We've done some additional characterization of the material. Again, the upper left graph is showing X-band loss. These are different samples that we construct in different ways, and they have different response characteristics. The material, also like velvet, if you know you have velvet, you can brush it, and you can see it reflects light in different ways. Well, the flock material, when we flock it, we can also give it a bias in one direction or not, make it kind of tilt one way or not, or make it completely random. And as such, then, we get a rotational bias in the reflection in the chamber. In the lower right-hand corner is showing more or less 3 samples that were more or less even, and one where we biased the flock, so it had a real strong response to various angles of incidence of the wave. And then the other unique prop, what I'm trying to say is it's anisotropic. So there's a different response from the front side of the surface to the back side of the surface, and there can be a rotational bias as well. So it's a little unusual. Most magrams it doesn't matter how you rotate them front to back. They're pretty consistent. With this, we can control that and vary it quite a bit. So we developed this great hammer, this material that really is a strong absorber. We went looking for an application. Somebody's got to want to buy it, or your startup dies, right? And so we were looking through different sources of funding, and discovered xTechSearch and the whole thing. And one of the needs was improved soldier protection and lethality. Better ways to enhance warfighters' survivability, provide concealment, avoid all these things, all the reasons why you want to keep people from being detected by microwave energy. And on the upper right-hand corner there's an image of the flock material I saw showed in the cartoon, where in this case, that is carbon fiber flock. That's what's called a stacked focused image. So there are 10 images stacked on top of each other, because the scale is so small you can only focus in a little bit. But from the side, it kind of looks like a dewy turf, like little beads of magnetic material, those little chokes on the carbon fibers. And so we said, okay, well, we have this carbon fiber. We know it absorbs microwave energy. We know there's a need to control EM detection of soldiers and equipment and so forth. How do we take our breakthrough in the lab and apply it to something that could be useful to the Army? And so we considered then liners for helmets, coatings for body armor, shelter systems that you might want to conceal from a microwave detection. ASSET covers ghillie suits, ponchos, whatever. So we said, okay, how can we adapt this to those uses? And so the project status is, the xTechSearch was a great way to focus our energy and drive to say, okay, let's make something useful that somebody wants to acquire. And so, here we are. So through the NSF they sent us to this mini I-Corps camp, where they really want you to focus on customer discovery and finding out what people want. And so we're in this iterative customer discovery process where we're asking people what they want. We faced a unique challenge because much of what the military wants and needs is classified. So the first question I'm always asked is, do you have a clearance? I don't have a clearance. And they say, oh. And then I say, well, what would you like to see? And they say, I can't tell you. And they say, just keep going. So, okay, we'll just keep going. So these are our best guesses onto what might be needed for soldier protection. So we're in this iterative loop where we prototype something, test it, see if it works out, and come back. And so we're up here at this capstone where we're showing some functional prototypes of how this material might be incorporated into things that are useful for the Army. So here's an example. This is an example, I should pass this out. This is MagRAM. So we're trying to compete against this material. It's magnetic RAM, it's a ferrite silicone. It's a silicone material loaded with iron, and it's very heavy and fairly narrow band, but strong absorber. This is an example of our concept piece of MF RAM. And in that sample, it's the paper that weighs the most. The actual radar absorbing component of that is just a few grams. The mounting weighs more than the radar absorbing material. Kind of a fiber surface, but it's not practical in the sense that it's rather delicate. It's not going to be abrasion resistant. You can't crush it. Needed to a format that would be more usable. So here's our development. We had this MF RAM, very drapable. We took it to an anode chamber. You can see some of those dielectric foam absorbers in the background. We just draped it over. We put the helmet on an aluminum plate and then draped the stuff over. And obviously, it's not very practical. It's a good absorber, but just not practical for soldier application. So what we did is decided to develop a tile system. We have a 3D printer. We could print these tiles out with the 3D printer. And you can see that we're holding that tile, which is this, something like this. This one's in Kevlar, but it's about that size. And just holding it up against the window, and you can see through it. So it's porous. It's breathable and extremely lightweight. I'll pass out a tile so you can see what one of these tiles looks like. That one's in Kevlar, I believe. So we print it, and that makes it much more robust, wear resistant, but retain its microwave. And then we can take those tiles and put them together. And then we looped them together with a mesh to kind of make a helmet cover. And again, that thing just weighs a few grams. And we'll demonstrate that later, the absorption response of that material. You can see, some of the coatings have a UV coating, so it lights up when he shows the material. So again, the first concept piece was to just put these tiles together, and we could tie them together and to create this kind of liner. Now that could be extended to a shelter system, the Alcans. There are many possible ways you could apply that. Very lightweight, robust, stable. So the helmet, and then we said, okay, what if you just wanted to make a very lightweight kind of cap that you would. And so that would be another, and this is MF RAM material is all incorporated in there. So it's just taking those tiles and then doing some geometry, and again, a concept piece, but only weighs a few grams and has very strong X and KU band absorption, greater than 10 PV. All right. So here's another development cycle. Maybe you want to tell us, maybe they're not interested in helmets. That's about the body armor. They have these IOTVs, these panels that are made out of Kevlar or other materials. And so again, we developed these what we call a mosaic, where we join them with silicon. So it's this flexible tile. And then we're just testing the response. Again, that's in the anechoic chamber. So they're just a a couple examples of how this might be applied to soldier protection systems, if that was it. Again, this is a materials technology, so it's not just limited to soldier protection, but that might be one application that might be of interest.
Did you consider tiles for vehicles, or how would you implement this on say, an armored vehicle?
There are a number of ways. I noticed in the display they had all cans over some of those vehicles. It could be, we'll demonstrate this, could be kind of integrated into the all cans. You know, this material we 3D printed, it's noisy, but you could print it in other materials that, you know, didn't make as much, you know, it's not a wind chime.
Right.
Yeah. But yes, you could integrate that into the all cans.
Okay.
And that's a Kevlar substrate with the absorber in it.
And the performance, the radar absorbing performance is the same regardless of the substrate, or does that vary?
It changes a bit. You know, the dielectric materials has, but still a very strong absorber, you know, generally greater than 10 dB and fairly broad range through X and K. And we've tested it up through KA.
Okay.
And, you know, 5 to 10 dB, sometimes much more. We have a feeling that actually, because the fundamental lengths of the fibers are typically between 1 and 3 millimeters, it's going to be very strong absorber in millimeter wave frequencies. And we see this kind of periodic response where it seems to hit the, you know, the wavelength multiple of the fibers we're using. And so if we're up in millimeter wave, it should be a very strong absorber. We can only test through 40 at this point. So we're trying to get a grant to get, you know, higher.
So you're confident that it's absorbing and not just scattering it?
Well, we can tell, yes, we think so. Okay.
And do you have any idea of the mechanism then for the absorption, or?
It's going to be a combination of insertion loss and magnetic loss then as well, because it has both of those materials, and you know, that's what the fundamental parent parameterization. And we continue to characterize the material. We're kind of still in the search space of saying, okay, how does this length of fiber affect the absorption? And we're trying to build that model so we can say, oh, if you want an absorber that absorbs really well at K-band, you know, 20.5 gigahertz, we say, well, then we have to use this amount of fiber and this length and so forth. So we're trying to get to that model.
Well, I mean, just understanding, so if you're absorbing that energy, whether it be microwave energy, where does it go? I mean, what, you know, what happens to that energy, and you know, how is it dissipated once it is absorbed?
It would be heat.
Okay.
Yeah, in the material itself.
Okay. Any idea of the temperature increase then in heat?
Well, we're working on such low power, you know, we can't measure where we are.
Okay.
I mean, we've stuck the material in the microwave in the office just for kicks, right? It does heat up a lot. You know, we stick the FLIR camera on it, so it's going in there.
Right. Well, I'm just thinking with, you know, with the vehicle, if you're trying to reduce its radar signature, but yet, you know, the absorption increases even enough of a temperature gradient that you increase its thermal signature.
Yeah.
You know, what's the trade-off in signature reduction where, you know, radar and now thermal IR, you know, you may end up creating a problem that.
Good questions. Yeah. And, you know, radar cross-section is both a function of shape, absorption, and then scattering, you know, how much you're redirecting away from the source of the beam to someplace else.
Right. So I didn't know if it was isotropically just scattering it, and so your loss is that way, or if it is absorbing, then
it's absorbed because we've made it, you know, we have stuff that's not so isotropic, you know, it doesn't matter on the angle, and it still, you know, absorbs very strongly.
Okay.
Okay, so why would you be, and again, this is a materials technology. I don't have just one application. It can be widely applied to many different problems in EM management. And you know, for a war fighter, this soldier protection, well, why would you be interested? Well, it's lighter. Everybody, we've heard several discussions today about reducing weight is just a darn good idea, you know, overall. Reduce fatigue, you know, more agile. You can carry this other stuff that you really want to carry rather than, you know, radar protection, and longer deployment. Improve signature management. I haven't mentioned this, but this material can be widely applied to other things other than soldier protection, to electronic equipment itself. And basically, if we're dealing with electronic signals, we have signal to noise ratio. And I have two ways to increase signal to noise ratio in an electronic circuit. Number one, I can increase the power, which gives me more signal, but then I need more energy on the input side to boost the power. The other way is to reduce noise, is to reduce the noise of the system. So signal to noise ratio, either boost the numerator to give me more signal to noise, or decrease the denominator. And so if I decrease the denominator, I get a boost in signal to noise without putting in more power. So it's an energy efficient material just by that. Also, it's lightweight. So in any mobile application where I have to move this material around, be an airplane, a vehicle, a person, it's going to be energy efficient because it's lightweight. It just doesn't take that much. It takes less energy to move the stuff around. So two energy efficiency boosts. And we've applied this to antennas, cables, circuit boards, enclosures, equipment, clothing. I mean, it has a myriad of applications in EM signature management. Okay, another, I said that has widespread application, and we'll do demonstration of this here. What this is using this material, because it's anisotropic nature, to create a lens for microwave energy. So this is a microwave lensing material. We can use this for beam forming and beam shaping for antenna systems. And we'll demonstrate this here. So on the left-hand side of that figure is this carbon fiber. We can harvest the carbon fiber flock. So that magnetized flock, we can dissolve the substrate, and we're left with these little, it's like lawn clippings. We end up with a pile of these lawn clippings. We can then put those in other materials, in this case silicon. And we align those in a certain way because they're magnetized now. We can align those fibers by applying a magnetic field. And when they're in the silicone before it's cured, we can line up all those little particles in a way we want them, and the silicone cures and they're set in place. And so in this case, we're making Fresnel zone plate lenses with this material to focus a microwave energy, and we'll have a display of that. I'll go over that next, so we'll show that, and I'm going to run out of time unless I keep going. So, again, as a metamaterial, it can be applied to multiple objectives that the Army has for modernization. So it's a lightweight radar-absorbing material. Any type of aircraft, vehicle, whatever, where you're trying to control radar return, it would be an option to consider for that use. Radar cross-section reduction. Again, next generation combat vehicles, same arguments would apply there. Any type of facility where you have lots of RF equipment, it can interfere with each other, so you have to kind of isolate different equipment and make sure it's not stepping on its neighbor. You can use these absorbers to manage that EM emissions from equipment to make sure that everything's functioning the way you want it. Long-range precision fires, any type of beam forming. Some beam, some lensing applications would have application to beam forming, and then radars and isolation. All those things can be addressed with these materials. So that's my presentation. thank xTechSearch. This has just been phenomenal experience, and I hope the Army keeps doing it. It's great, and just meeting the other companies here and talking to other individuals has been fantastic. Got a lot of really good feedback, and it's been really good. Also, I have to acknowledge the National Science Foundation gave us the seed money to kind of SBIR phase 1. We're waiting on our phase 2. We've applied. We'll figure out if we can get a phase 2. Business Oregon applied some of this equipment that we're going to use here. State University has been our partner. They have an EM lab and professors who know about EM. I do fluid mechanics, so this has been a stretch for me. But we know, and thank everybody here for their time. So, questions?
You have demos?
Yeah, we have demos. So, Adi and Kent, would you like to come up and do the demos here? So, on the left, I think we'll first demonstrate. This is kind of a small-scale NRL loss test. So what we have here are 2 antennas. These are KU band antennas, the 12 to 18 gigahertz antennas. One's a transmit antenna, one's a receive antenna. And so we're sending microwave energy down to that plate. The plate is a perfect reflector, a metal plate. It's going to reflect 99.9% of that energy, and it's going to be picked up by the receive antenna. So,
did you know that whenever judges approach your that you will have a period of confusion? Please, oh great.
Always. You're almost guaranteed. I think did Steve Jobs or Bill Gates say that? Likelihood of failure during live demos directly proportional to the importance of the people you're demonstrating it to.
There you go. Here we go. All right.
So the baseline is it's just basically showing there that we're bouncing energy off that plate, microwave energy and it's scanning between 12 and 18 gigahertz. And it's just saying we're basically getting almost total return from that. It's our baseline.
What you're seeing here is the reflection loss, and the green line there is sort of the baseline we took in Portland, and things change when you travel, and the angles change. And the purple line is sort of the live response you're seeing now, and that's sort of the response with the aluminum plate, the soldier helmet.
So the helmet and that stuff is absorbing. It's absorbing a bit of that energy.
And then I think Ken's going to throw an observer on top.
RCS testing's a little different. Then I get to fire the target, spin it around, and I also get it.
Let's demonstrate because we're going to run out of time and we have a bunch of demonstrations. Yeah. So again, that's with the.
So you're getting about I think 10 dB on average, a little bit more. That would be greater than 90%.
90%, 99%.
Yeah, 10 dB. Yeah, 10 dB is about 90.
It's logarithmic.
Yeah, 90.
It's logarithmic.
So what's the cause of these peak absorbances?
Inside of that resonator, it's a resonator, and I have a 2 millimeter cavity. I matched my resonator with the size of the fibers.
Let's move on, though. Let's move on because we're going to run out. We only have 10 minutes. So do you want to show the IoT, here? This is the flexible, plate. So this is, and again, it's a prototype. So, it's a little delicate. It's our first one. But this would be like the vest insert, something you might want to put in the vest. Again, it's extremely lightweight. Most of the weight in that is actually in the silicone glue holding the tiles together. That's what weighs. And,
We know every gram in the warfighter is important, so we better offer significant advantage.
yeah, we'll put this on the plate.
Same concept, you're checking reflection loss.
Partial plate.
Partial plate. So then, it's got interesting behavior. Different angles of attack, different performance. This can be tuned and controlled.
This particular group is made to be like leaves. They are semi-reflective, semi-translucent, semi-absorbent. So it depends on your angle of incidence.
Okay. All right.
He'll translate more.
And then
I understand.
here's some other applications. You know, if you're detecting somebody, you're looking for Doppler shift. And here are the absorbers just applied as, you know, because if you're moving and your arms are moving, that's going to be easier to detect. So here are just some, you know, again, a concept. How would we apply this to soldier protection? I don't know if it
A
be.
woodland environment is what this system was designed for, to simulate foliage and make it grow again. You don't look like a black spot, you don't glow.
Right.
You just look like what you're around.
Yeah. So you try, you know, edge detection is always big, you know, so it would obscure the edges and make it harder to see the Doppler.
And the material is all the way out to the edge of your tile? Or is it,
That little hole runs through it. It's right at the edge.
We have a partial.
We will be getting it wider, but
It's not 100% coverage. There's a lip around the tile because we don't want to crush it, so there's a little lip on the tile. So it's not 100% coverage, but 90% coverage, yeah. And then the last thing we want to demonstrate here is the lensing. Yeah, this is the really big thing. We're very proud of this.
But we didn't know it was that important.
So I remember I was at Playa Vista and I passed this out and somebody was like doing like, can you have adjustable? And I was like, oh, I think so. And so here's a demonstration of using this as an adjustable lens. So what that is just a cavity. There's the two Fresnel zone plate lenses. We have a way to pressurize the cavity to deform the lens. And so we can change the focal length of the lens using these absorber materials. And so
You can see it's a slightly curved plane way.
Showing the
We are right at the edge of the ear.
So this is C-band, 4.8 gigahertz, 4.4. And this is just a device that's showing what kind of electric,
Wavefront.
yeah, wavefront. And so, you know, that's
right now it's the baseline.
that's the baseline.
We can throw our lens,
Put lenses in there.
show your heat signature pop up.
And so it's kind of a heat map of the intensity of the electric field. And you can see then we've concentrated that energy in a small spot. And then if we inflate the lens, we can deform the lens, and you can see we can change the response. We can focus that energy, so it's an adjustable focus lens. So somebody asked me, can we make these?
Sorry, I have to get a little heartbeat to it.
It's
We used to have
leaky.
hard clamps on this, but some of the folks got really big on it, and it got to, I was afraid it was going to fail. So I put the rubber bands. He suggested the rubber bands. We
The rubber
can't
band is
overrun
an
it.
easy pressure release system, so we don't blow it up.
It's the pressure cooker with the safety relief valve, so we don't blow our Fresnel lens. But again, it's a concept just to show how these things can be deformed to manage microwave energy. There's broad application beyond just, you know, a helmet or, you know.
And then we were working on the transmit side.
Yeah, so the transmit side, so that would be a Fresnel zone lens that you would stick over. And again, you could deform that. It's the alpha version.
You actually find this is a wide-angle lens. I'm sorry.
Yeah.
But if you look at this,
Yeah,
you have handedness disorder. It's a bear, okay? When I made it so it looked like his sister. But then I realized, no, it doesn't look like his sister. He's supposed to be upside down.
So the Fresnel lens should be.
So this is a wide-angle attachment right now. But if, you know, in theory, you could put silicone in here, and so you'd have a dielectric lens because you'd have it thicker and thinner areas. You could go ahead and use air, which I use to deform just the two members and not worry about the dielectrics and keep your curve. Or you can go ahead and run the solution through here, whatever you want, to cool this if you're running at high power, because this is an absorber. It's not a bad one to do a whole lot. Most of what I'm trying to do is just edge things around. I'm not trying to, come on, everybody, go around. And so it should be able to handle, we throw it in a microwave. That's how I test it.
That, yeah, we have a low power office microwave. It was cheap. I got the $50 microwave. I think it's 800 watts.
I haven't blown it up yet. And believe me, we've done some fun things in there. Sparkaroo. Any more questions or anything?
So, I guess have you worked out the pressure to, you know, curvature rate for the lensing, or just
Not that much.
Yeah, we were just like, oh, this is, can it work? Is this
Right.
a and so we're at that.
Okay.
You know,
Yeah, we were
this
trying
is,
to see what we can do with waste material.
yeah, this is the leftover from that stuff, you know, it is like,
We start looking
waste not, want not.
Another, putting like picket fences around the front, kind
Edge control, we're also trying to do side lobe
of
reduction.
some eyelashes and some eyebrows. So this is the piece that shows that. Which is unfortunately backward. But I'll make the one correction next time. But it does work.
So again, in summary, metamaterial, microwave management, multiple applications. Our challenge is getting people to tell us what they want.
We will try to.
Okay.
And if you tell us what we want, we can try to make something for you.
And we can get our clearance as soon as we have anybody tell us what, you know, you have to have a sponsor for clearance.
Yeah, you can't,
When you have no thing, you have no sponsor.
it's a catch-22,
It's a
right?
catch-22.
Yeah. So we did our guess. We just, you know, we read what's published and we're discussing.
I watched some old TPN 25, ANTPN. It's a ground surveillance radar from Vietnam.
Oh, yeah. You know, some of the 60s becomes unclassified. That's what we can find, you know. So we're 50
Right to
years.
Vietnam.
Yeah, we're 50 years behind.
No, I think I'm good.
Yeah, we're down to 3 minutes. Wow, I didn't think I'd take that much time. Well, thank you for your time.
Thank you.
Thank you.